And with that, good morning everybody. Welcome back to Power On Edge. And welcome back to campus, those of you who ended up traveling over the weekend. Welcome back to Real Analysis. Hope you all are doing well. Plan for today is we're going to change course a little bit, and instead of talking about how do we show individual sequences converge, we're going to start talking about how do we prove properties hold true in general for convergent sequences. So what can we say about all convergent sequences instead of individual ones, for instance? I've got my usual office hours for the next few days, 11 to noon and 1 to 2. Homework 4, as I mentioned earlier, is due on Tuesday now. So if you have it for me today, great. If not, just make sure you get it to me or to my mailbox outside my office door by the end of the day tomorrow. And yes, there is going to be a homework 5, and I'm currently thinking homework, and I'll probably post it later today or tomorrow, but it will be due Wednesday next week, is the plan. Just to give you all a bit of a heads up as far as exams go, I'm thinking Friday after spring break will be our our in-class midterm. After spring break, not before, because my 9 o'clock class was going to mute me if I told them they had to do an exam right before spring break started. Y'all, they're very rambunctious crew. I'll announce that formally once we get closer to the time, but that's currently the plan. So, does anybody have any questions or comments before we get started today? Do you all know that we're supposed to get over an inch of rain today? Apparently that's a thing, so apparently we're getting some heavy rain today. At the moment it doesn't look too bad, but it's gonna be getting rough later.
There's some good puddles that I watch for you.
Yeah, rained a fair bit earlier. Right now it's in the middle of a little bit of a lull. So with that in mind, 2 lines are caught outside when it starts raining. What should they do? Clearly, if 2 lines are caught out in the rain, they should coincide. Okay, so last week we focused a lot on looking at our definition of what it means for a sequence to converge. We talked about and said intuitively, a sequence A sub n converges to A if, as n gets really, really big, A sub n gets closer and closer to A. And we had a more formal way of saying that we were using, that A sub n converges to A if for all epsilon greater than 0, there exists a big N, a point in the sequence past which every term that follows has distance from A that is less than epsilon. Meaning that absolute value of A sub n minus A eventually needs to be less than epsilon for every term in your sequence past a certain point. So, for instance, just as a quick reminder, for this sequence I drew on the board here. Emily, for the epsilon I drew, for this specific error tolerance, what would be a value of big N we could choose so that past that point, every following term is within distance epsilon from A?
3.
Yeah, we could say, for instance, if big N is equal to 3, then for all little n greater than that, for all little n greater than 3, the distance from A sub little n to our A is going to be less than that epsilon. Meaning A sub n is within distance epsilon from A. So last week we kind of focused on looking at individual sequences and talking about the question of, given this sequence, how do we prove that it converges by constructing a proof of this sort of thing? Or how do we show that a sequence fails to converge? So what we're going to do today is start talking about properties of convergent sequences in general. Things like if you take 2 convergent sequences and add them together to get a new sequence, is that also going to be convergent? Or if we add a divergent and a convergent sequence, is that going to be convergent? Or what can we say about convergent/divergent sequences and things like whether or not the sequence is bounded or whether the sequence is monotone? that's kind of going to be the focus of the next few classes, is trying to construct mathematical theorems and proofs related to these things. So with that, got a new packet for y'all. Actually, I'm just going to pass you back to this one. So what I want to focus on today is looking at the relationship between a bounded sequence and an unbounded sequence, and how does that relate to properties of convergence. So let's take a look-see. I want to look at the sequence a sub n equals 1 minus 1 over n, and the sequence b sub n is equal to, let's say, n squared. So if we start writing out what do the terms in this sequence and each of these sequences look like, for a sub n sequence, we're going to get 1 minus 1 is 0, 1 minus a half is a half, 1 minus a third is 2/3, 1 minus a fourth is 3/4, etc., etc. for our top sequence. For our bottom sequence, we're going to get 1, 4, 9, 16, 25, etc., etc. Now, if I were to try and graph the terms in these two sequences, in the first sequence, we get a set of points that look something like, well, between 0 and 1. Here's our a sub 1. Here's our a sub 2. Here's our a sub 3. Here's our a sub 4. Hey, look, I'm actually putting the dots on the number line this time, because some of you all have been complaining about me not doing that. And we're going to get terms that do something like that. Whereas for our b sub n sequence, well, we're going to have one at, b sub 1 is going to be at 1, b sub 2 is going to be way out here at 4, b sub 3 is going to be way out here at 9. I'm not going to try and draw any more than that. Visually, what can we say about the terms of these two sequences and how the terms appear to be behaving differently from each other? Lincoln?
In a sub n, the subsequent terms are getting closer and closer together, and in the b sub n sequence, they're getting further and further apart.
Yeah, these terms seem to be getting closer and closer to each other. The b sub n terms appear to be getting further and further apart. Specifically, if I were to ask you, let's see, Evan, if I were to tell you intuitively, one of these sequences is bounded, the other sequence is unbounded, which one would you guess is the bounded sequence?
Probably a sub n.
Why a sub n, intuitively?
Because you can see it definitely doesn't go off to infinity, but n squared does go off to infinity.
Yeah, we can see that this sequence kind of is going off to infinity. In fact, the terms are even getting further and further apart from each other. It's growing pretty fast. Whereas this sequence, oh, it's also growing. As n gets bigger and bigger, these terms keep getting larger and larger and larger. But these terms don't go off to infinity. They're kind of trapped between, they're all trapped between 0 and 1, in fact. And that's going to get us into our definition of boundedness for a sequence, where we sort of talked about boundedness before with regards to sets of numbers. With the sequence, intuitively at least, we can say that a sequence is bounded if it doesn't go off to infinity, if the terms don't get like infinitely or arbitrarily large, which does happen with our b sub n, so this will be an unbounded sequence. But our a sub n sequence is actually going to be nice and bounded. Jackson, did you have a question?
No.
Okay. So, just like with sequence convergence, saying a sequence goes off to infinity is kind of not really mathematically very precise. So we're going to try and come up with a more precise definition for what it means to have a bounded sequence. I've actually already written it up on that sideboard there, but just to remind you, or just to put it up on the front so we can talk about it. We're going to say that a sequence A sub n is called bounded. So I apparently butchered this in the packet, so you'll have to make a couple changes. We're going to say that a sequence A sub n is bounded if there exists some n greater than 0, where n may or may not be an integer, could just be any real number, such that the absolute value of a sub little n, not x sub little n, is less than or equal to big M for all little n in the natural numbers, elements of n. So in other words, we're going to say that a sequence a sub little n is called bounded if we can find some constant number so that the absolute value of every single term in our sequence is less than or equal to that constant number. So Nick, for instance, if we look at this sequence a sub n, what would be a value of big M that we could choose that we would say every term in the sequence has absolute value less than or equal to that big M?
2.
Big M equals 2? Everyone on board with that? Yeah, I would agree. We could say that this is bounded, for instance, by, big M equals 2. Every term in the sequence has absolute value less than or equal to 2. Now, could we have chosen a big M that's smaller than 2? Ginger?
1.
Yeah, we could have chosen big M equals 1 even. Every term in the sequence does have absolute value less than or equal to 1. I also could have chosen big M equals, 5 billion if we felt like it. Because every term in the sequence has absolute value less than or equal to 5 billion. But the moral of the story is the fact that we can find at least one big M that is greater than or equal to the absolute value of every term in the sequence. Thus, we say that this sequence is a bounded sequence. Any questions or comments about that? So, Dr. Gerstle, when we talked about sets, we said set's bounded if it's bounded above and below. How does that relate to sequences? You could equivalently say if the sequence is bounded above and below, then it's a bounded sequence. That would be an equivalent definition to this. But having a single value big M to talk about here is going to be useful for us once we start proving theorems using this boundedness condition. All right. 3 sequences, bottom of the page 1 in the packet. Go ahead and take a minute or two, talk to your neighbors, and for each of these, I want you to determine whether or not you think that sequence is bounded. And if it is bounded, what would be an example of a big M you could use as a bound for that sequence? Let's go ahead and take a couple seconds. As always, talk to your neighbors and see what you can make of these three sequences.
Second one.
It's really just the first one. Like you said that this
And writing.
Take your time, Gary. Like, I'm a class.
So,
what's up, man? This felt like the cheap guy.
Yeah, but you like. We'll go by.
So on something a little more interesting, we can take the 4 about n plus 0.1.
Does the N mean?
Actually, maybe it looks a little more visually interesting, I don't know.
Or n times pi times e times the golden ratio.
Yeah.
I think it's.
N times pi times e times the golden ratio. Sure. That would have a much harder time writing out individual terms in that sequence, but it would behave similarly, yes.
Yeah. You're not like a single number. Or like
You said you could always reduce that. Wait, I'm getting there, I'm getting there.
We all doing up here? Especially for the third one, you may think, how would you prove it?
Well, I mean, it could be any,
About
it could be, but if you create a set of
Doesn't necessarily need a
sequence, then one has.
Could do a proof that way if you wanted to, don't necessarily have to.
Yeah.
When you think of it, you're gonna be writing 2 and.
By 1, yeah.
So like.
I'm just listening.
Yeah, that was so true. So like.
Write it down.
True is the number that's spoken in class. So that.
I wouldn't go that far.
Zombie show.
Got the same boundary.
Interesting.
So it'll always be like.
You could also use big M equals 50 for both of them, if you wanted to.
A lot.
Here's my question.
Well, it's exponential, like, it's like linear one.
Serve out for that sequence. Just find all of them.
Yeah.
Find all of
And
them.
do all my.
Okay. In a finite amount of time, how could you prove
Yeah, you can always have a bigger.
that big amount?
Becomes bigger all the time.
Hey, you're drinking bigger.
Doing
Doing great?
I'm a little tired, but I'm good.
Okay, fair enough.
Please prove that you share
Not until you have your PhD in math. Meaning I can't, you can't.
I get emails.
Yeah. And I have one.
Oh, yeah, that's always telling me about those, I'm like, these emails, go to Nick for some.
I think it's like.
I'm trying to send an email to Nora, I accidentally almost sent it to you. That's harder because you all have like the same first initial. Like, wait, Interlure, that's not hard. Because it's showing me that email doesn't mean that's one I should use.
Because then you.
Yeah, and it does for this minus, and then you put it down.
You're just making it, but that's how we make a relationship between those numbers and show.
Yeah. What if like the ends on the power, you can't do like ends.
Alright, y'all doing? Bit better?
It's hard to prove.
I took a good day.
Oh, there we go, now we're
Or the sector last week, I didn't see
I'm ready, I'm ready.
Not exactly, it's just.
Your cranky little lad. Alright, I'll have to try and push some buttons and see what reactions I can get from you.
True.
Alrighty, let's come back together and talk about these sequences. So let's start with 1 over 1 plus n. Jackson, what did you think about this one?
It's bounded.
It is bounded?
Yeah.
Okay, by what?
1/2.
He said big M equals 1/2 bounded?
Yep.
Well, let's see. We start listing out the terms in the sequence. We'll get 1/2, 1/3, 1/4, 1/5, etc., etc. Everyone agree that that's going to be bounded by n equals 1/2? I would agree. term. N gets larger and larger, terms in the sequence are just going to keep decreasing. So the first term is the biggest one you're going to get. Mary Beth, how about the B sub n equals the floor of n? What do you have to say about that one?
It's unbounded.
Unbounded? Okay. How can we simplify writing out B sub n is the floor of n? Is there a way to simplify that at all?
Yes.
Cool. Elaborate.
You could say that it's the set of natural numbers.
Yeah, it's just going to give us natural numbers. Or in other words, floor of n is really just a fancy way of saying n. If n is a natural number itself, it's going to equal its own floor. Let's put the floor in there for a little bit of extra pizzazz. So that's going to be the sequence 1, 2, 3, 4, etc., which is unbounded. In fact, the fact that the sequence is unbounded is precisely what the Archimedean property says. How about this sequence? D sub n equals n over 2 to the n. I think this one's a little bit trickier. Lincoln?
It's bounded by 1/2.
Bounded by a half?
Yeah.
Let's write out some terms. Let's see, if we plug in n equals 1, it's going to give us a half. If we plug in n equals 2, it'll give us 2/4, which is also a half. If we plug in n equals 3, we'll get 3/8. Plug in n equals 4, we'll get 4/16, that's a fourth. We'll get 5 over 32, etc., etc. Lincoln, what makes you say the sequence is bounded by a half?
I mean, it's, with the exception of the first term to the second term, and both of those are equal to each other, it's decreasing after.
Yeah, it appears to be decreasing after. How do we know that this sequence is going to be decreasing? Maybe the first 5 terms were a bit of an anomaly. Emily?
Because the denominator is growing at a faster rate than the numerator.
Ah, the denominator is growing faster than the numerator? Yeah, we could say this is going to be bounded by a half. I agree. We could say that the sequence is decreasing, at least weakly decreasing. Weakly meaning each term is less than or equal to the term that came before it. Weakly decreasing since 2 to the n grows much faster than n does. At least for n greater than or equal to 2. If you wanted to, you could make that, we could even make that more of a formal proof by looking at something like, let's look at the function f of x equals x over 2 to the x, and then show for x greater than or equal to 2, f prime of x is less than 0, which would say that the sequence has to then be decreasing. The terms are getting smaller as x in general, or n in this case, gets bigger and bigger. Any questions or comments about any of the sequences? It feels like you have an amusing thought.
I just like, that would be a nasty group then.
Not that one. Oh, okay, now we have to. Not that bad. I mean, what, f prime of x is low d high minus I d low. Let's go to the x again. Oh yeah, it's natural log of 2 times 2 to the x. Nearly, let's go down below. Which, we can do a little bit of simplifying. Say 2 dx times 1 minus x natural log of 2 all over, this 2 to the x cancels out one of these, so 2 to the x, and then we could say that's negative if 1 minus x natural log of 2 is negative, which is the same as saying x natural log of 2 is greater than 1, which is equivalent to saying x is greater than 1 over natural log of 2. Ah, there you go. That's so bad. Do you remember your quotient rule, Caleb? Goodness gracious. You're gonna have a fun time towards the end of the semester then. No, maybe in a couple months from now, maybe in like April sometime, I'll put that on the homework, prove the quotient rule. It's actually not that bad to use product and chain. So, question. Anybody notice anything about all of the sequences that we say are bounded? Specifically, what do these two sequences have in common? Actually, what do these 3 sequences all have in common that B sub n and B sub n do not? Emma?
They're fractions, or they involve a fraction.
So do these.
They have an n in the denominator.
They have n's in the denominator, okay. But more specifically, not in terms of how the terms look, but like properties of these sequences, let's say. Parker?
Well, other than them being bounded, they all seem to approach 0.
Yeah, they're all convergent. I don't think this one approaches 0, but I think that one.
Well, they all, yeah.
I think that one's converging to 1.
those
Those
two
two
go
converge
to
to
0.
0. But more specifically, they all converge. So here's a question. Without turning the page, you cheater, what relationship do you think bounded sequences and convergent sequences have to each other? First of all, do bounded sequences have to be convergent? Lincoln?
No, because if you look at the sequence, -1 to the n, that is bounded, but it is not convergent.
I see. So you're saying, for instance, if we write this out, running out of variables, let's call it C sub n. Let's skip C sub n for some reason. If we call C sub n -1 to the n, which is just a sequence -1, 1, -1, 1, -1, 1, etc., etc. You're saying that that is a bounded sequence that is not convergent? Yeah, I would agree. And it's going to be bounded by big M equal to, give me a value for a big M for that sequence. 7. Every term in this sequence has absolute value less than or equal to 7. I agree. But not convergent. So you can have bounded sequences that are not convergent. But can you have convergent sequences that are not bounded? Turns out the answer to that one is no. So let's prove it. Turns out every convergent sequence has to be bounded, in fact. I'm going to erase our bounded definition even though we're going to need it. Don't worry, it's still up on the sideboard over there. Next to the terrible derivative. So that's a big theorem of the day. Every convergent sequence is bounded. So, a showery process. So let's prove this. So how do you think we would prove such a thing? Obviously, we can't go through and check every single sequence individually, one by one, because there's infinitely many sequences we can define. Uncountably infinite, in fact. Emily?
Could we use the definition of convergence and then show that the thing that it converges to has to bound the function, or bound the sequence.
Ooh, show that the thing it converges to has to bound the sequence? Could certainly try that. Fortunately, I don't think that's going to work because, for instance, if we look back at our 1 minus 1 over n sequence, or actually, no, that's not a good example. Let's just look at 1 over n. That converges to 0, but I would argue 0 is definitely not going to be a big M that works for this sequence. Reason being, each of these terms is it's bounded by 1, but the sequence doesn't converge to 1.
A bound is not an upper or lower bound.
Correct. Yeah, the lower bound is 0. It's not going to have an upper bound. 0. Lincoln?
I could try supposing a convergent sequence is not bounded and then prove by contradiction.
Try a proof by contradiction, eh? Ooh, that sounds spicy. Yeah, I tried to write a proof by contradiction of this over the weekend. Ran into some trouble. Actually, I think we're going to do a direct proof on this one, but instead of looking at any specific sequence that we have in mind, we're going to take an arbitrary convergent sequence and then show that we can somehow construct a bound on how big that the terms in that sequence can get an absolute value. So let's start off by letting a sub n be a sequence such that a sub n converges to a. So we're going to take an arbitrary convergent sequence. Other than the fact that it's convergent, we're not assuming anything about what it's converging to or whether it's like an increasing or a decreasing sequence. We're just assuming it converges. And we'd like to define a big M that'll work for that sequence, meaning every term in the sequence has absolute value less than or equal to that big M. So what does that mean? A sub n converges to A. Well, if A sub n converges to A, that's going to tell us, by definition, for all epsilon greater than 0, we can find a big N such that yada, yada, yada. Notice that if the sequence converges, that tells us for any epsilon that we want, we can find a big N that works for that epsilon. Any epsilon we want. Isabel, give me an epsilon greater than 0. Okay, epsilon equals 1. Let's stick with it. In my last class, you'll learn more. Then we can say for instance, I don't know, epsilon equals 1, we know there exists some big N, a natural number, such that if little n is greater than big N, the absolute value of a sub n minus a is going to have to be less than 1. So the fact that a sub n converges to a tells us that for any epsilon I can find a big N that does what I want. So what I'm going to do is I'm going to take Isabel's suggestion and say, all right, if I can do this for an arbitrary epsilon greater than 0, I'm just going to do it for epsilon equals 1. If it works for any epsilon, it should work if I pick out a specific one. But I can find, meaning we can find a point in the sequence, a big N, past which the distance from a sub n to a is always going to be less than 1, specifically. Then for little n greater than n, we know that 1 is going to be greater than absolute value of a sub n minus a. And there I'm just rewriting, I'm just flipping around this inequality. I claim absolute value of a sub n minus a is going to be greater than or equal to absolute value of a sub n minus absolute value of a. Does anybody know what that what result tells us then? Spencer?
Is that the triangle inequality?
It is indeed the triangle inequality. Yeah. So there's a theorem in math. blessings, that says for any, and this is kind of as an aside, it's not really part of this, we're using this result in order to prove this. But what the triangle inequality says is that if A and B are any two real numbers, then the absolute value of A plus B is always less than or equal to absolute value of A plus absolute value of B. Or another way to phrase it would be to say that the absolute value of A minus B is always greater than or equal to absolute value of A minus absolute value of B. So why is that called the triangle inequality? Lincoln?
It's just like how with a triangle, the biggest side is always less than or equal to the sum of the other two sides.
Yeah, that's exactly it. So if we think about this, let's say in terms of vectors in R2, or Lincoln in terms of complex vectors if you want. A way you could sort of visualize this would be to say, let's say we're defining a triangle like this. Okay, an angle like this. Let's call this vector A to get from here to here, and this is going to be vector B to get from this point to that point. Then the vector A plus B is just going to be the vector we would get from completing this sort of triangle. And the whole idea of A plus B has size less than or equal to size of A plus size of B really is just saying visually that the length of one side plus the length of the second side is always going to be greater than or equal to the length of the third side. In fact, it's going to be a strict inequality unless you have a degenerate triangle that's really a line segment in disguise. So this shows up a lot in real analysis. We're actually going to be using this result quite a bit throughout the semester. Let's see who's had a bunch of classes. Isabel, you've had a bunch of classes with me. We're not going to prove this result in class. Why do you think that is? Why would we skip a result in class?
Oh, it's gonna be on the homework.
Number 1 on homework 5 is going to be proving triangle inequality. Don't worry, it's not too hard to prove. You don't even need epsilons or anything for it. But I'm going to borrow this result today, and we're going to use this result plenty more times to kind of give us to break up this absolute value of A sub n minus A into absolute value of A sub n minus absolute value of A. Or another way to restate this, if we added, say, absolute value of A to both sides, would be to say that the absolute value of A sub n is always going to be strictly smaller than 1 plus the absolute value of A. And if you notice, A sub n corresponds to a term in the sequence. What we're saying is that the absolute value of the nth term in the sequence is going to be less than a constant. 1 plus the absolute value of A. So, Lincoln, what's troubling you?
Well, you dropped the equal, but couldn't A be equal to 0, or?
Absolute value of A?
Yeah.
Sure, absolute value of A could be 0. The fact that 1 is going to be strictly greater than this line because of this inequality here.
Yeah.
If all that we had was 1 is greater than or equal to that, then we'd have a less than or equal to here. But the fact that 1 is strictly greater than this line tells us that you have strict inequality. So here's a question. What we were looking for is a constant, the big M, so that for all natural numbers, the absolute value of A sub n is less than or equal to M. Does this constant here that we found fit the bill? A constant that all the terms in the sequence have absolute value less than that. Evan, you on board? Katrine, you on board? Parker, you on board? Nick, are you on board?
Kind of.
Kind of. Explain.
I don't quite get it yet, but.
So it turns out that this constant m, or this constant, which I haven't named yet, does not work for our m necessarily. So why is that? Why can't we use, we got the inequality we want. Why can't we say that this constant works for our m? Spencer?
I mean, we're taking our little n at some point in the sequence, but it's not necessarily at the furthest point from what it converges to.
Yeah. Problem is, we don't know that this inequality holds for every little n in natural numbers. We only know that it holds for little n greater than big N. So what that means is, if big N is, say, 6, then the 7th term and onwards in this sequence are all going to have absolute value less than this constant. The 7th term and onwards do, but the first 6 terms don't necessarily have to. So this constant works for almost every term in the sequence, all but a finite number of terms, in fact. But it doesn't quite work in total. All right, fine. I'll call it n hat then. It's not going to be the n we want, but, let's give n a hat. Or, on a day like today, let's give n a rain jacket or an umbrella or something. So, we know the 7th term in the sequence and onwards, if in the case where big N equals 6, are all going to have absolute value less than this constant in the hat. So how do we find a constant m that works for every term in the sequence and not just for the 7th term and onwards? Because I think we can use this m hat, it's just not quite the finished product that we need. Lincoln?
Well, since epsilon could be ultimately a very, very large value, you could find some value for it that would work for n is equal to 0.
But I don't want to use epsilon as a large value, I want to use Isabel's value, epsilon equals 1. Turns out that if you change epsilon, you can change what value your big N is, but you're never going to be able to be sure that your big N can be 0 necessarily. Jackson?
I was going to say, you can find the maximum of all the preceding terms to the big N.
Take the maximum of all the preceding terms and then the n hat?
Yeah.
Turns out that's going to be what we're going to do. So let's take a look at the sequence one more time. Thank you, triangle inequality. We'll be referring back to you later. And I'm not going to prove it, but you all will prove it. So let's consider the sequence a sub anything. If we start writing out terms, we'll get like a sub 1, a sub 2, a sub 3, blah, 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 a sub big N, a sub big N plus 1, a sub big N plus 2, etc., is going on forever. We know all of these terms that all of the terms past a sub big N, so a sub big N plus 1, a sub big N plus 2, according to this argument here, all terms here are going to have absolute value less than or equal to. In fact, strictly less than, but all we really need is less than or equal to our m hat. So Jackson, it sounds like what you're proposing is we take the maximum of these terms and m hat and have that be our big M? That's going to be what we're going to do, yeah. So let's let big M be the maximum of absolute value of a sub 1, absolute value of a sub 2, absolute value of a sub 3, up through absolute value of a sub big N, and m hat. And what do we know about this big N? Well, we know A1 has absolute value less than or equal to absolute value of A1, and absolute value of A1 by definition is less than or equal to our big M. We know A2 has absolute value less than or equal to, well, absolute value of A2, which in turn is less than or equal to our big M, from how we constructed our big M to be the maximum of this set of things. A sub 3, same idea. A sub big N has absolute value less than or equal to absolute value of A sub big N, which is less than or equal to the maximum of all these terms. A sub big N plus 1 has absolute value less than or equal to M hat, which has which in turn is less than or equal to M from how we defined it. A sub big N plus 2, A sub big N plus 3, etc. All of the terms past A sub big N have absolute value less than this M hat, which is less than or equal to our M. Thus, let's say then, for all natural numbers, this time we're not saying bigger than big N, or getting big N involved in any way. You can say for all natural numbers, the absolute value of A sub n is less than or equal to the maximum of all of these values, our M. And so, A sub n is in fact bounded. There's our proof. Yes, Ginger?
Do the parentheses just denote that it's a sequence
What?
around A sub n?
Yeah, whenever we put A sub n in parentheses, that's like how you know we're talking about the sequence A sub n and not like an individual term in the sequence. If you ever see me write like that, that means the nth term in the sequence A sub n. And yes, I realize that there's a little bit of, oh, we use A sub n to refer to the nth, to a single term and also to the sequence as a whole, and I agree the notation's a bit weird. Get used to it. I have a question for y'all. Why did we need to get this n hat in the first place? Why couldn't we just start off our proof by saying, let m be the maximum of absolute value of A1, absolute value of A2, absolute value of A3, etc., going on forever? Why couldn't we just say that at the very start of our proof and just said immediately, oh, then every term has absolute value less than or equal to n, therefore the sequence is bounded? Spencer?
If you didn't include M hat, you'd have to check for the maximum of an infinite number of terms.
Yeah. So if we have an infinite number of terms, if I have a set with infinitely many real numbers in it, does that set necessarily have a maximum? It could, if the set's like 1, a half, a third, a fourth, a fifth, etc. That set has a maximum. But it could also be a set like the natural numbers that doesn't have a maximum to it. So this may not be, this may not even exist. Because there's infinitely many terms. Whereas, in how we defined M up here, how many terms are there that we're taking the maximum of? Lincoln?
There are n plus 1 terms, I guess.
Yeah, there's big N plus 1 of these. But what we really care about is that there's a finite number of terms. And the fact that there's finitely many terms means we can take the maximum. If you give me 10 real numbers, I can take their maximum. Caleb, if you give me 1 billion real numbers, might take me a while, but I could find their maximum. Point is, any finite set of real numbers is always going to have a maximum to them, but an infinite set of real numbers may or may not have a maximum element. So that's why we couldn't just do this right off the bat. That's why we needed to get our n hat, is to say, well, we have some finite number of stragglers that could ruin the pie, but all the rest all have absolute value less than this m hat. So since we only have, big N plus one of these terms, that's a finite number, we can take the maximum of the finite and many terms. But if our sequence wasn't convergent, then we couldn't necessarily find this big N hat, and so we couldn't necessarily find the maximum in this case. All right, have a good day, everybody. I'll see you all on Wednesday. So on Wednesday, we're going to use this boundedness property to prove that if you form new sequences from adding or multiplying old convergent ones, you're still going to get something convergent. And the proofs on Wednesday will be more similar to the ones from last week, I think, than this one was. Have a good one, everybody. See y'all on Wednesday. Don't forget, if you have your homework now, you're welcome to turn it in. If not, just make sure I get it by the end of the day tomorrow. All right, thank you.
Lame. Linear operators are lame.